In this video, we're going to introduce you to finding zeros of polynomials. And the first thing that I want to discuss with you is the difference between a zero and an x-intercept. There is a subtle difference, but there is a difference. So a zero is any value of x that solves the equation p of x is equal to 0, where p of x is a polynomial. So if I plug in for a value for x and I get out 0 for y, then x is a 0. And a 0 can be complex or it can be real. Now, the x's that you plug in and get out 0 that are real are going to be your x-intercepts. So your x-intercepts are the real zeros. So if x is a real number and I plug it in and I get out 0 for y, then that number is going to be an x-intercept. So all x-intercepts are zeros, but not all zeros are x-intercepts. Okay, this first example will illustrate the difference between the two. I think it's a good example to show the difference. So we are going to first start off by factoring x to the fourth minus 16. We're going to find all the zeros, and then of those zeros, we're going to state which ones are x-intercepts. So we're going to set this equal to 0 and solve for x, because remember, zeros are the x's that solve the equation p of x is equal to 0. Well, if p of x is x to the fourth minus 16, we set that equal to 0 and solve for x. So I'm going to go ahead and factor this. This is the difference of squares, so I would have x squared minus 4 and x squared plus 4. Now this is another difference of squares, so I can factor that again into x plus 2, x minus 2, and I can't factor the x squared plus 4 over the rational numbers, so I'm just going to leave that as is. Okay, so to break this down, since we can't factor it over the rationals, I'm going to take x squared plus 4 and set it equal to 0. And then that is going to give me x squared is equal to negative 4. And then I square root both sides. So I get x is equal to plus or minus 2i. Because I get plus or minus the square root of negative 4. And because the square root of negative 4 is 2i, and then I have plus or minus because the square root is plus or minus. So here are the two zeros for this factor. Then when I set each of these equal to 0, right, if I set up all my little mini equations, this is going to give me negative 2, and this is going to give me positive 2. So these are all zeros. So my zeros, I have 4 of them, plus 2i, minus 2i, negative 2, and positive 2. Those are all my zeros because any of those values, if I plug it in to p of x, I'm going to get out 0. However, the only two here that are x-intercepts are my real x's, which is negative 2 and positive 2. These are my x-intercepts. And if I look at the graph of x to the fourth minus 16, it's going to look like this. It's going to look similar to a quadratic. It's just going to jump up faster, and it's going to cross at 2 and negative 2. you're not going to see the numbers 2i and minus 2i on the real coordinate plane. That's not going to show up there. You're only going to see the real values. So although all four are zeros, only the real values are going to be x-intercepts. Okay, so now let's go on to the remainder theorem. The remainder theorem says if p of x, a polynomial, is divided by a factor, we'll call it x minus c. So c is just some number. It could be 4, it could be 2, it could be negative 3. Okay, so I have some factor, x minus c, and I'm dividing it into p of x. And there is a remainder r, we'll call it remainder r. Then if I plug in this value here of c, I'm going to get out the value r. So the remainder when you divide by that factor is going to be related to the value when you plug in that value of c. That's going to be your function value, your corresponding y value. So notice that I'm plugging in a positive c here, even though this has a minus here. It's x minus and then this number. So whatever you plug in is going to be the opposite sign of what's in the parentheses. Okay, so let's do an example to show how this works. It says if p of x is equal to negative x squared plus 3x minus 2, then p of negative 2 is equal to negative 12 using the remainder theorem. So the remainder theorem says if p of x is divided by x minus c, this is my c, so I'm going to have x plus c because it's a double negative. Well, in this case, let me actually put the number in there. It would be x plus 2 because it would be x minus a negative 2, so that gives me a plus 2 with a remainder r. Then p of negative 2 is equal to r in this case, which is negative 12. So we're going to just show that by division. So I'm going to use synthetic division. So if p of negative 2 is equal to negative 12, then when I divide p of x by x plus 2, then I should get a remainder of negative 12. So I'm going to put negative 2 in my box. I'm going to write down my coefficients. So I have negative 1, 3, and negative 2. Those are my coefficients for my polynomial. I'm going to first start off by carrying down the negative 1. So I have negative 2 times negative 1. That gives me a positive 2. Then 3 and 2 is 5. Then I take negative 2 times 5, and I get a negative 10. And then when I add that, I get negative 12. There's my remainder. So it works. So if I take x plus 2 and divide it into my polynomial, or if I take negative 2 and plug it into the polynomial, either way, I'm going to get negative 12 for the remainder and for the value of the function. Okay, the vector theorem says if p of c is equal to 0, then x minus c must be a factor of p of x. So if I plug in a value and I get out 0, so c would be the value, the x value that I plug in, just some number, and I get out 0, then c has to be a 0. And if c is a 0, that means x minus c has to be a factor, because I want to be able to plug in c and get out 0. Okay, the next thing that I want to talk to you about is the rational zero theorem. And we're going to use this theorem to break down and find some possibilities for rational zeros for a polynomial. And what the rational zero theorem will do is, instead of looking at all the rational numbers and trying to check all of them with the polynomial, it's going to break it down so that we only have a handful to check. But before we get into the rational zero theorem, I want to quickly review with you what a rational number is, so that this makes sense to you. So a rational number is any number that can be written in the form P over Q, where P and Q are integers. Okay, so for example, 1/2 or -3/4 or -2, +100, 0.333 repeating. These are all rational numbers because they're all numbers that can be written as a fraction. Now these are obvious because those are already written as a fraction, where the top and the bottom are integers. Whole numbers can be written, or integers can be written as a fraction, because all I have to do is put a 1 under them and it's written as a fraction. Repeating decimals can be written as a fraction. For example, 0.333 repeating is 3/9. And then of course, if you have repeating decimals, or if you have terminal decimals like 0.5, that's a terminal decimal. It stops. It doesn't go on forever and it doesn't repeat. So it's terminal. 0.5 can be written as a fraction. It's 1/2. So anything that can be written as a fraction is considered a rational number. So now going on to the rational zero theorem, if we have a polynomial, p of x is equal to an x to the n plus an minus 1 times x to the n minus 1 all the way to a0. So then let p be any factor of AO, which is your constant, this last number, and let Q be any factor of AN, which is your leading coefficient. Then possible rational zeros are all combinations of P over Q. So if I take all the possible factors of the constant and divide them by all the possible factors of the leading coefficient, that will gives us a list of the possible rational zeros of that polynomial. And then we will use that to narrow it down. Instead of looking at all the rational numbers and having to check all of them, this narrows it down to a handful for us to check.